yesterday we discussed several measurements, constraints, upper limits on variation of alpha, and a little bit also on other couplings. Today we're going to mainly see how these measurements can be used to constrain specific cosmological models and fundamental physics models. But before that, I want to say a little bit more about measurements of the CMB temperature, which I also talked about briefly in the last couple of days. But even before that, just one slide summarizing the constraining power of measurements of alpha in a model-independent way. So as I said, we'll see constraints on specific models in a few minutes. But in principle, there is another way of using these measurements, which is to take a cosmographic approach. Now, I don't know if you're familiar with the idea of cosmography, which exists generically in cosmology. So the idea is that instead of choosing a particular cosmological model whose parameters you're going to constrain, you use a model-independent approach. So you take quantities like the scale factor, for example, and you write it as a Taylor series, so as an expansion around present day, redshift 0. And then you're going to constrain the coefficients of that series. So if you think of the series for the scale factor, then the linear term of that series, so the first derivative will be the time derivative of the scale factor. So that's going to be the Hubble constant. Then the quadratic term is going to be the deceleration parameter. The cubic term is going to be the jerk parameter, and so on. So instead of constraining specific parameters of specific models, you just constrain the parameters of this series. This has the advantage of being model independent. It has some disadvantages, such as having to decide when you truncate the series, how many terms in the series you keep. And also, if you're using data beyond redshift 1 and you expand in redshift, then mathematically there is no guarantee that your series is going to converge. So you can read about that later on if you want. For our present purposes, we're going to follow this approach and take all the measurements of alpha that I discussed and write possible variation of alpha as one of these Taylor series, as you see in the slide. So delta alpha over alpha is going to have a linear term, a quadratic term, a cubic term, and so on. By definition, the monopole is 0 because delta alpha over alpha is alpha at some point minus alpha today divided by alpha today. So by definition, this value is 0 today. So you write a series like this, but because of this problem of convergence of the series, it's not a good idea to expand in redshift. It's better to expand it in what's called the reduced redshift sometimes. So this is this quantity y, which is the redshift divided by 1 plus redshift. So this is always less than or equal to 1, so you don't have the problem of convergence. And you can take all your alpha data and use it to constrain the coefficients of this series. And the reason why this approach is interesting, other than being model independent, is that the linear term is basically the rate of change of alpha, so alpha dot over alpha, and that's going to be constrained by local tests, by the atomic clock tests that are done in the lab, which I mentioned yesterday. Whereas the higher order terms are going to be constrained by astrophysical observations. So in a sense, you separate the effect of local constraints from the effect of astrophysical constraints. Now, if you do that analysis, you get the constraints that you see on the right side of the slide. So A1 and A2 are the linear and quadratic coefficients of this series. And in the top part, you see constraints that you get if you truncate the series to quadratic order, so if you ignore the cubic term, and you get the 1, 2, and 3 sigma constraints. You see that there's no statistically significant evidence for deviations from 0. The constraints on A1, so the first term, are much stronger. They're fraction of a part per million, and this is the power of the atomic clocks, as I mentioned yesterday. Constraints on the quadratic term are at the few parts per million level. And here I have black and red contours. The red ones are what you get from the archival data, so the data from Webb et al., which is archival data, is data not taken for this purpose, and therefore potential issues of calibration and so on. The black ones are from dedicated measurements, so measurements that were taken specifically with this purpose in mind, so with the purpose of measuring alpha. And therefore, these are measurements where calibrations were done in a more sophisticated way, where this error modeling has been done more carefully and so on. And in principle, they are the most reliable ones, or at least in the sense that you can estimate systematic uncertainties as well as statistical uncertainties. You see, there's a difference between the two data sets. Even for the Webb data, there is no statistically significant preference for no variation, but you do see these differences. So that's the top part, the top panels. The bottom panels are what you get if you expand the series to cubic order, but then marginalize the third coefficient, A3, and derive constraints on the plane of A1 versus A2. And you see there's no significant difference again, which tells you there's no need to include a cubic term again, because there's no evidence for non-zero values of the first two coefficients. So this is a nice way of encapsulating all the measurements and putting them all together in a single constraint. Essentially, what dominates these constraints are the atomic clock measurements for the linear coefficient and the quasar measurements for the quadratic coefficient. In the paper that we wrote last year, we also included constraints from the CMB, from Big Bang nucleosynthesis, from Oklo, and so on. But all these constraints are subdominant. So what dominates is atomic clocks and quasars. So this is another way of saying something that I mentioned yesterday, which is that for the purpose of constraining these models, the CMB constraints are relatively weak. Okay, now let me spend a few minutes talking about these measurements of the cosmic microwave background temperature. So we all know that cosmic microwave background has a black body spectrum to an excellent level of approximation, and you all know, I guess, the current temperature of CMB, the 2.7260 Kelvin. So this is a cosmological measurement, but you can also measure it in the galaxy. But this is a measurement of the CMB temperature at redshift 0. It doesn't tell you anything about how the temperature behaves at non-zero redshift. Basically because it's not so easy to do those measurements. But it is possible to measure them. And one reason for measuring them, in addition to just generic scientific curiosity, is that in the standard cosmological model, if you assume that the universe is expanding adiabatically and the photon number is conserved, then CMB temperature has the redshift dependence that you see on the slide. It's inversely proportional scale factor, so it goes as 1 plus redshift. So this is a prediction of the standard model, but this behavior is violated in a lot of extensions of the standard model. And one example of these are models or alpha variants. So again, the way that this relation will be changed will be model dependent. One simple way of modeling these changes is something that Lim et al. Proposed in the year 2000, is just to say that the exponent in the term 1 plus z is not unity, is 1 minus some coefficient beta, and then you can use data to constrain this beta coefficient. Okay, so if you want to measure the CMB temperature at non-zero redshift, how can you do it? There's essentially two ways. So one is to use the Sunyaev-Zeldovich effect, so using galaxy clusters. That gives you measurements at low redshifts, low redshift 1 typically. But high-resolution spectroscopy allows you to also do these measurements, and typically at slightly higher redshifts. So you can do these measurements using quasar absorption spectra if you see transitions whose fine structural levels can be populated by CMB photons. So if you have photons with the appropriate temperature, with the appropriate energy, that they can populate some of these energy levels. And if you measure, if you identify these transitions in your spectrum, uh, then you can extract the temperature of these CMB photons. If you can also subtract the effect of all other astrophysical processes that can excite these transitions. So actually, the first measurement of the CMB temperature, which was an indirect one, which was done by McKellar in 1941, uh, essentially used this method. They measured the CMB temperature in the galaxy using a CN transition, and that led to a temperature of 2.3 Kelvin at the time. And actually, CN, so it's an excellent thermometer. It's extremely sensitive to the CMB temperature. Unfortunately, we cannot use it cosmologically, at least right now, because there's no CN identified outside the galaxy. It has also been identified in the clouds, I believe, but there's no, it hasn't been identified at cosmological distances that you could use to do this measure. So in the absence of CN, you use other species, other atoms or molecules, uh, which have some transitions that can also be excited by CMB photons. And again, the principle is the same. If you see these transitions on your spectrum and you know enough about the physics of the cloud where this absorption occurs, then you can extract measures of CMB. So you can use neutral carbon, and this has been done. These measurements have been done since the year 2000. Um, but carbon has the disadvantage that the levels which can be excited by CMB photons can also be excited and populated by other astrophysical processes that are just intrinsic to the local environment. And sometimes you cannot disentangle the two. You cannot subtract the non-CMB effect, and therefore what you can really get is an upper limit for the CMB temperature at that range. It's not really a measurement or a detection of the temperature. On the other hand, CO, carbon monoxide, is a much cleaner probe, um, because essentially it's systematics free. There aren't that many mechanisms that can provide alternative sources of excitation. There's some corrections that you have to make in this analysis, but they are comparatively small and fairly well understood. So for the moment, CMB temperature measurements using carbon monoxide are the most promising way to go. And essentially, they are signal to noise dominated. You can improve constraints just by accumulating more photons. Of course, someone has to give the telescope time to do that, but that's a that's a different matter. There is one caveat, which is that it's not actually that easy to find quasar absorption spectra where you can see these CO transitions in a way that allows you to make the measurements. There's about 6 good ones, 6 lines of sight where these measurements have been done with an uncertainty, so with an absolute error bar of about 0.7 Kelvin to 1 Kelvin. And there's a few more which are not so good, where the error bars are slightly larger. So all these measurements are pre-espresso. It is possible in principle to improve these measurements a little bit with espresso, and we are working on it, but we don't have results yet. There is also a measurement using molecules, so not using optical spectroscopy, that has been done by Mueller et al. So this is a measurement at much lower redshift, so redshift 0.9, but it has an uncertainty of only 0.1 Kelvin. So it's a tighter constraint, but it's lower redshift. And on the bottom right, you see a summary of all these measurements or upper limits on the CMB temperature as a function of redshift. So notice that some of the green points are upper limits, not measurements. So on the low redshift part of the plot, you have measurements from Sunyaev-Zeldovich effect. On the higher redshift part, so between roughly redshift 1 and 3, you have measurements coming from this quasar absorption spectroscopy. And you can see that if you parameterize possible evolution of CMB temperature as just a straight line with some slope, then you can get uh, fairly reasonable constraints on this slope at the level of 1% or so. Um, and actually, these CMB temperature measurements now play a useful role in cosmology. So on the right side of the slide, you see a couple of plots from a paper that three students of mine and I wrote last year. Leah Gale is the first author, which looks at constraints on a particular model. We don't need to worry right now what kind of model it is. It's essentially a decaying dark energy model, or a model where cosmological constant is not really constant, but it decays with some power of time. So you see the usual plane of omega matter versus the effective equation of state of dark energy. And you see three sets of contours, so 1, 2, and 3 sigma contours. So blue ones come from supernova data, so the Pantheon data set. The green ones come from double parameter measurements from baryon acoustic oscillations and cosmic chronometers. And the red ones are from these CMB temperature measurements. So both the Sunyaev-Zeldovich ones and the spectroscopy ones. And you can see you get pretty decent constraints, and moreover, in this plane, the CMB constraints are pretty much orthogonal to the cosmological constraints. And in black, you have the combined constraints from the three data sets, and you see there you can get really tight constraints and basically break degeneracies that you otherwise have between these two parameters. On the bottom right, you see the result of a very simple simulation which illustrates the constraining power of the Andes spectrograph, which is being built for the LT. So it's the set for this person. We'll talk about it a bit more tomorrow. And what I've done here is it's just a very simple thing, which is to assume that I keep all the other data fixed, but I improve the spectroscopic CMB temperature constraints by remeasuring them, by reobserving these sources with Andes. And so therefore, I'm going to get a tighter constraint, and I translate those constraints into constraints on this model. And you can see there's a very significant gain in constraining power. So the point I want to make here is that these measurements of the CMB temperature are already quite constraining, and they can be competitive with other low redshift cosmological data sets. Not for all models, because in some models the evolution of the CMB temperature is a standard one, and therefore in those cases adding this data set will not give you anything more. But for models where CMB temperature is affected, such as models or alpha varies, then these constraints can be significant. But you can go a bit further, and this is something I also mentioned on Monday. Not only the temperature redshift relation is changed in these extensions of the standard model, but the distance duality relation is also changed. The relation between luminosity distance and the angular diameter distance, which in the standard model is just 2 powers of 1 plus redshift, is also changed in these models. So in this case, the assumptions are a metric theory of gravity and again photon number conservation. So this will not be the case if alpha is varying. You can also logically parameterize these deviations if you want by putting in a parameter epsilon here and add it to the power of 2. And just to illustrate how these two things are related, you can actually show that in a broad class of models, this parameter beta, that is the temperature redshift relation, and the parameter epsilon in the distance duality relation are not independent. You can actually show that in some models, not all of them, beta is just minus 2/3 epsilon. So they're not independent. What this means is that you can use CMB temperature measurements to constrain distance duality relation and so on. So there's this consistency between these kinds of tests. And current constraints on these kinds of things, so on distance duality relation, are sub-percent level. There's a recent Euclid paper on that, looking at these constraints. I'll get back to it in a moment, later today, if I have time. And actually, these distance duality constraints are important overall for Euclid. So for Euclid data, um, it's important to check whether or not the distance duality relation is preserved when you do various Euclid data analysis. Okay, so now let's get on to the connection with cosmology and to the use of these measurements in constraining specific classes of cosmological models. And again, the motivation, I mentioned pretty much all of these on Monday, but let me just summarize it for you again. We know the universe is dominated by some unknown component, which is accelerating it. That component has a gravitational behavior that is very similar to that of a cosmological constant. But given the fine-tuning problem that you have, if you want to have a cosmological constant, you may argue that a scalar field is a more likely explanation. Personally, I would subscribe to that argument, but we can debate it. Personally, I think it's a reasonable argument. Now, we don't know what this scalar field is until we actually find it. But we do know it must be slow rolling, at least close to today, because you need a negative pressure to acceleration. And you know, or at least you expect, that it's dominating dynamics today. And this is enough to guarantee that this scalar field, if it is coupled to the rest of the model, which you expect to be the case for the reasons I mentioned on Monday, then it should lead to observable long-range forces and varying constants. So what this means is that whatever measurements of alpha I have, even if they're null results, even if they're upper limits, will be important because they will help you constrain these models and restrict the parameter space that you might otherwise have for these models. Another important point is that this scalar field will, if it's coupled to electromagnetism, it will also couple to nucleons, because part of the mass of the neutron and the proton comes from the electromagnetic sector. So therefore, this will lead to a weak equivalence principle violation. So any model where alpha is varying unavoidably violates the weak equivalence principle. And therefore, so we can use these constraints on alpha and also constraints on the weak equivalence principle to set cosmological constraints on various kinds of models. Now, you can also ask a question, which in a sense is, how low should one go? By which I mean, at the moment, the sensitivity of quasar measurement is at parts per million level, and we're finding upper limits. So therefore, you can ask, well, if Espresso doesn't see anything, it doesn't detect any variations, should we push any further and try to improve even more the constraints? Or if you want to phrase it in a more pragmatic context, if Espresso doesn't see anything, is this still a science case for Andes and for the LP? And I think the answer is obviously yes, but let me walk you through that argument in some detail. So here, the interesting analogy and the point to keep in mind is the comparison with constraints on the dark energy equation of state. So if you have a cosmological constant, then the equation of state of that component is -1. If you have a scalar field giving you dark energy, it's not. And you can measure and constrain this dark energy equation of state, which I'm going to call W0 here. But actually, from a fundamental point of view, the physically relevant parameter is not really the equation of state. It's 1 plus W, 1 plus the equation of state. Because if you have a scalar field, that will be essentially the ratio of the kinetic energy of the field, or the speed of the field, to the total energy density of the field. So essentially, it's telling you how fast is the dynamics of this field. And the cosmological constant is the limit of a scalar field with zero speed. So it's the limit of a scalar field which is not moving at all. Now, if you have a scalar field in your theory giving you the dark energy and accelerating the universe, naively, there's no parameter in the theory that would fix the value of 1 plus W. So naively, you would expect it to be of order 1. But observationally, we already know it's less than 0.1 or something like that. And then the point is, if this number is not of order 1, and if there's no natural scale in the theory to fix this number, either that there is some fine tuning that makes this number be really small, much smaller than 1, or there is some symmetry of nature, which we don't know, that forces this number to actually be 0. Okay, so this argument you can make of dark energy equation of state, of 1 plus W, you can make the exact same argument for alpha. If you have a scalar field coupled with an electromagnetic sector, that will give you a variation of alpha. And naively, that if there's no natural scale for this variation, you would expect the order of magnitude of delta alpha over alpha to be of order 1. Observationally, we know that this delta alpha over alpha, if it's non-zero, must be less than 10 to the minus 5 or maybe a few times 10 to the minus 6. So again, if this is very small, it's either fine-tuned or there's some symmetry of nature that forces it to be 0. So going back to the question, should we push beyond parts per million? Yeah, the answer is yes. And here we can take a second analogy, which is something called the strong CP problem in quantum chromodynamics. Some of you, maybe many of you, might not know what this problem is, but don't worry about it. Essentially, what this is that in particle physics, there is a parameter which naively would have expected to be of order 1, but experimentally, we know that it's less than about 10 to the minus 10. And trying to explain what this number is and why it's so small is a big problem in particle physics. The simple way to try and explain it is to postulate something called the Peccei-Quinn symmetry. But if you postulate this symmetry, it will have other implications. One implication is that this symmetry gives you a possible dark matter candidate, which are particles called axions. So essentially the point is, if we keep pushing these bounds down, even if we don't see anything, if we don't detect any variation, this will either imply that there is no dynamical scalar field on cosmological scales, and that's an interesting result in and of itself, is telling us something non-trivial about nature, or there's some symmetry of nature that we also don't know about, which suppresses these couplings to the rest of the theories. Maybe the scalar field is there, but doesn't give you a variation of alpha because this coupling to the electromagnetic sector is forbidden because of some reason which we currently don't know about. So one way or the other, by pushing these bounds down, we learn something new about nature. Okay, so there's several different ways of classifying possible cosmological models, and in particular, dark energy and modified gravity models. And one classification that I like was proposed by Jean-Philippe Pouzin. There's essentially 4 classes of models. So models on the left are models where gravitational spectrum is not modified. In models on the right, the gravitational sector is modified. Models on the top part, or in models of the top part, the field that the new physics is dominating the dynamics. So on the top left you have quintessence fields. On the top right you have scalar tensor theories, for example. Whereas in the bottom part, the new dynamical degrees of freedom are not dominating dynamics, are not dominating the expansion of the universe. So for example, in the bottom right, you have models where dark energy is a cosmological constant, but You have a variation of alpha, for example, and you violate distance duality. For our purposes in these classes, um, we can make do with a simpler classification and just divide the models into two classes. And I'm not going to be very inventive in this point. I'm going to simply call them class one and class two. Um, and class one class one contains the models where the same degree of freedom, so the same scalar field, gives you both dark energy and the variation of alpha. So in a sense, you can say these are the simplest models because you just have one new degree of freedom, and that degree of freedom does two different things for you. So they're economical models in this sense. Now, if this is the case, so if the same degree of freedom gives you both variation of alpha and the dark energy, then if you know the evolution of dark energy, so if you know how the field evolves as a function of redshift, uh, then you know the variation of alpha and you can relate it to the evolution of dark energy. So in this case, the evolution of alpha is actually parametrically determined. And in fact, you don't need to know the underlying dynamics of the scalar field. You don't need to know the scalar field potential, for example. All you need to know is the equation of state of the field. So in these models, variation of alpha as a function of redshift, so delta alpha over alpha, is given by this expression. So this zeta is essentially the coupling of the scalar field to electromagnetism. So it's a particle physics parameter. Um, and then you have an integral, which essentially depends on cosmology. So it's the integral of a function of the dark energy equation of state and this omega phi, which is the fraction of the energy density of the universe in the form of dark energy. So it's rho dark energy divided by rho dark energy plus rho matter plus rho radiation. So if you know the dark energy equation of states, if you know W, you also know omega, and therefore you also know this integral. So this is what I mean by saying that the evolution of alpha is parametrically determined. Um, this also means that I can use cosmological measurements to constrain uh, these models, um, but I can also use measurements of alpha to constrain the dark energy equation of state, because I have this relation. Of course, I have this coupling, which is a particle physics parameter, and there will be degeneracies between the two sectors. Because to have a non-zero delta alpha over alpha, as you can see in this equation, I need two things. I need zeta to be non-zero, and I need 1 plus W to be non-zero. Right? So if W is minus 1, if I have a cosmological constant, then this integral is always 0, and I get no alpha variation. So you can see it immediately. So I need two things to happen at the same time in this class of models to have a variation of alpha. So zeta must be non-zero, and the equation of state must be different from minus 1, at least in some range of redshift. But that said, this is actually a very good way of constraining these models, and one can show that you can use alpha measurements, if they are sufficiently tight, to distinguish between various classes of dark energy models. So those of you familiar with dark energy models will have heard of freezing models and thawing models, but don't worry about them if you don't know what they are. The point I'm making is that you can actually distinguish between different classes of dark energy models by using alpha measurements. So one example of a class of models that can be constrained this way is the so-called CPL parameterization of dark energy, Chevalier Pollack-Linder. And you've done this recently in a paper by the Espresso Consortium. And you see some of these constraints on the plots on the right. So at the top, I have the 1D posterior likelihood for the dark energy equation of state, W0. And the green dashed curve is the constraint that you get from low redshift background data, so supernova data, baryon acoustic oscillations, cosmic chronometers, etc. The black line is the constraint that you get by combining cosmological data with astrophysical measurements of alpha and with atomic clock measurements. So actually, for these models, the atomic clock constraint is the tightest one individually. Local constraints from Lewis equivalence principle, from microscope, satellite experiment, and others also play a role. But astrophysical measurements also provide a significant weight in these constraints. And in the bottom right, you see the 1D posterior light fluid constraint on this coupling zeta, and this coupling is constrained at the parts per million level. And again, this is a strong statement because naively, your particle physics expectation would be that if this coupling is non-zero, it should be of order 1. So here we're restricting it to parts per million level. Okay, so that's class 1. Class 2 is the other class of models. So in these models, the dynamical degree of freedom that gives you the variation of alpha does not give you the dark energy, or at least does not give you all the dark energy. It's a subdominant. So in this case, it's typically you still have a cosmological constant giving you the dark energy, or most of it, but you have the scalar field in your theory in such a way that it has a small cosmological role, but it gives you variation of alpha. Now, if you use your cosmological measurements and combine cosmological data with alpha measurements on the assumption that the same scalar field is giving you both, you'll obviously make a mistake if the model of this class turns out to be the correct one. But you can actually test whether or not this assumption is consistent with your data. There's internal consistency tests that can be made. So there's several examples of models in this class. Perhaps the best known is a broad class of models called Bekenstein models. So this includes more recent models like the Olive-Pospelov model and so on. I don't have time to discuss them in detail, and probably many of you are not so interested in it, but there's papers written on this class of models that you can look up later. Here again, you can get extremely tight constraints. So you have a short table and a corner plot from a paper recently published, led by Leo Vacher. And you can see that so in these models, you can have different couplings to different sectors of the theory. You can have a coupling to baryons, a coupling to dark matter, and coupling to dark energy, and so on. And these couplings can be different. They don't have to have the same value. And even for the coupling to dark matter, this coupling is already constrained by alpha data and others to parts per million level. And the coupling to baryons is constrained to level 10 to the minus 13. So these are extremely strong constraints. Now, these Bekenstein models can also be used to illustrate the importance of where you do these measurements in terms of redshift and the constraining power of different spectrographs and telescopes. So this is a little bit of a side note, which is relevant for Andes, but I think since I'm talking about Bekenstein models at the moment, I think it's worth making a 1 or 2 minute digression to discuss this. So in this plot, you see a forecast of constraints that you can get from alpha measurements from different spectrographs and telescopes in these Bekenstein type models. And what is plotted in the two axes are constraints on the baryonic matter, so on visible matter if you want, and constraints on the dark sector, so dark matter if you want. Don't worry about the units in the axis. What matters is the relative constraints, not the absolute values. And in the black and solid and Nash contours, you see the constraints that you can get from espresso, so from current or forthcoming espresso data. In the colored lines, you see the constraints that you expect with the next generation of telescopes, so the GMT, TMT, or the ELT. And specifically for the ELT, there's 3 different contours, 3 different ellipses, which have been obtained under different assumptions on the blue coverage of the Andes spectrograph. So at the time I made the forecast, it was still called Iris. Now it's called Andes. And what this shows you is that having significant coverage in the blue is crucial. This is what will determine how powerful Andes is as a machine to constrain these kinds of models. If we don't see the blue, So if we start at 0.43 micron rather than 0.37 or something like that, then you lose a huge amount of constraining power. So seeing as much of the blue as is possible is essential for this kind of science. I'll come back to that point tomorrow, but since I'm talking about Bekenstein models at the moment, I think it's a good time to start making this point. Um, but actually, using alpha measurements to constrain these models can give you more than that. And in some cases, it might be the only way you can possibly have to distinguish some model from a cosmological constant. And one example of that is a class of models called rolling tachyons. So a rolling tachyon is a particular kind of a Born-Infeld scalar. So those of you who don't know what these things are, just pretend that last 30 seconds didn't exist. So pretend I didn't say this. Um, all you need to know for this purpose is that these kinds of scalars are well motivated in string theory. They exist in string theory. They unavoidably lead to alpha variations. Um, and these models are actually relatively simple because they have a very small number of free parameters. Essentially, in these models, there's a potential that the scalar field sees, and the slope of this potential determines both the dark energy equational state and the variation of alpha. And by combining cosmological data with measurements of alpha, so both astrophysical ones and atomic clock ones, you get constraints on the dark energy equational state, like the one you see on the slide. So 1 plus W is to be less than 2.4 times 10 to the minus 7 at 99% confidence level, so accuracy. What this means is if this model is the correct model for the universe, you will never see this with cosmological observations. There's no current or future cosmological data from supernovae, CMB, baryon acoustic oscillations, you name it. No cosmological data set will ever detect a W this small. But nevertheless, a model like this could still give you a variation of alpha at the parts per million level, or a large fraction of that. So you could still detect a variation of alpha for a model like this, and this would be the only way you distinguish this model from a cosmological constant. And these models actually do have one prediction, at least, is that delta alpha over alpha is always negative in the past in these models. So as you look back in Redshift, you can only find, if this model is correct, a smaller value of alpha. You cannot find a larger value. And there's a technical reason for that, but you don't need to worry about that. You can also test broader classes of string theory models. So this is part of a collaboration with current and former students of mine, also with Niels Schoenberg in Barcelona. So we looked recently, for example, at the class of models called runaway dilitons that are proposed by Lamour, Piazza, and Veneziano. And again, this can be constrained very tightly nowadays using alpha and other data. In these kind of models, you would again expect couplings to be of order unity, but these are already so couplings of other unity in these kinds of models are already ruled out. These couplings have to be less than 10 to the minus 1 or 2 times 10 to the minus 2. You can alpha measurements also have a role to play in what's called the swampland conjecture. Again, you may or may not have heard about this, but it basically a statement or a conjecture in string theory which says that you cannot have a cosmological constant in string theory. So if string theory is correct and the swampland conjecture is correct, then dark energy cannot be a cosmological constant. String theorists debate whether or not the conjecture is correct, but one way or the other, this is something that is now testable in principle. And again, I refer you to these papers if you want more details on it. So this is just to make the point that all this data is extremely constraining for a lot of extensions of the standard model. Now, since I mentioned possible spatial variations of alpha yesterday, Let me also spend a couple of minutes mentioning at least one model um, where these variations exist. These are called symmetrons. There's other examples of that, like chameleons. Symmetrons are perhaps slightly more interesting. Um, so in these models, what you have, so you don't have uh, time variations, but you have spatial variations, or more accurately, environmental variations. So you have a value of alpha that depends on the local density. So what happens essentially is that as the universe is expanding and you start forming structures, initially you have a uniform value of alpha everywhere in the universe. Um, as you start forming structures in the linear regime, the local value of alpha just depends on the density contrast. But then these structures start becoming nonlinear, you start forming galaxies and clusters, and these objects decouple from the background evolution. And in these objects, the value of alpha also decouples from the background evolution. So once you get to the nonlinear regime, the behavior of alpha is rather messy. You can only calculate it numerically. But in any case, you end up with special variations. And on the plots um, on the left, you have the usual sky maps. These come from n-body simulations. And what these show you is the value of alpha in different directions on the sky. And uh, so the bottom plot would be what you get at redshift 2. This is redshift 1. This is redshift 0. And you can see that in collapsed regions, you have different values of alpha from the background left. So in these models, for example, the value of alpha in a low density absorption cloud along line of sight of the quasar would be different from the value of alpha on Earth, just because density on Earth is much larger, and the Earth is inside a galaxy and so on. So one possible way of testing these models is to calculate a 3D power spectrum for alpha. So just like you calculate your matter power spectrum when you look at information, you could do the same for alpha. Um, and essentially the normalization and the kind of shape of the power spectrum would be different for different models. In the linear regime, all models would look the same, but once you get into the non-linear regime, then different models will behave differently. Question of how you could probe the linear regime in this case, and how you disentangle the effects of alpha from all the other messy stuff that happens in nonlinear regime is a good one, and I don't have a good answer for it. But in principle, this is something that might also be testable in the future. Okay, so let me just before finishing make a couple of interludes to relate this with some other cosmological context, and in particular to the Euclid satellite. So you all saw, I hope, yesterday the beautiful images of Euclid that were publicly released. So the background image I'm using today is one of these images, or part of one of these images. And being part of the Euclid consortium, I've been thinking a lot about how you can use Euclid data to test some of these models, and conversely, if the correct model is one where distance duality is violated, for example, how would that impact Euclid data, and how, to what extent would these kinds of things need to be taken into account in Euclid pipelines? So specifically for distance duality relation, Euclid in combination with other surveys can actually improve constraints on distance duality relations. There's a paper we wrote a few years ago. Matteo Martinelli was the first author, which first looked at current constraints on distance duality relation, combining all data that I mentioned already, and we actually managed to improve constraints which then existed by about a factor 2.5. But the main point of the analysis is to provide some forecasts for how well Euclid can do in improving these constraints on distance dwelling. And the result is, or the answer is that with parametric methods, so choosing specific models, uh, specific parameterizations of dark energy and of this distance population, you can expect to improve current constraints by about a factor of 6. Um, if you use non-parametric methods, so machine learning, genetic algorithm type methods, the constraint is the improvement is slightly more modest, but still it's significant. It's about a factor of 3. The same more or less can be said for varying alpha. So what happens to Euclid constraints? Uh, if you have a dark energy model coupled to the electromagnetic sector in a way that I described, and therefore leading you to a variation of alpha. So here, if you assume at least it's a class 1 model, then you can use alpha measurements and atomic clock constraints and weak equivalence principle constraints, um, added to the cosmological data, so to the Euclid data, to constrain these models. And you can ask by how much does this improve? And the result is that including alpha measurements improves the Euclid figure of merit on dark energy by between 8% and about 26%, um, depending on what is the correct fiducial model. So depending on whether or not there is actually a detected alpha variation, or we just have a null result, so an upper limit. And the reason for this is actually, well, first simple, but second also interesting. It's just that it gives you a redshift lever arm. So with alpha measurements, you can go much higher in redshift than with cosmological data like Euclid's. Um, and this is illustrated in the plot in the bottom left. So this comes from an earlier analysis, also done in Euclid context, but uh, at a much earlier stage of Euclid, so 2012, in 2014. Um, so what you get is, what you see is constraints on the W0, WA plane, so the usual two parameters in the CPL parameterization of dark energy, and the green contours are the 1 and 2 sigma constraints on W0, WA coming from quasar data. And you see that superficially they're not very constrained, right? You have big contours. Uh, the red ones are the constraints from all non-QSO data, so cosmological data. And you see you have a tight constraint on W0, but a relatively weak constraint on WA. When you combine the two, you get the purple lines, and you vastly improve the constraint on WA just because alpha data allows you to go much deeper in redshift, and WA is essentially parameterizing how the equation of state can be changing with redshift. So this redshift lever arm helps you a lot. So this is essentially the reason for the gains in sensitivity uh, that you get when you combine alpha data with low redshift cosmological data. It proves the dynamics at higher redshifts. And remember that in a lot of models, these fields are slow rolling, so they're moving slowly. And if you want to detect something that is moving slowly, you're much better off by looking at it for a long time or for a long redshift. Um, let me also make one other side remark, just to provide some context. Um, all these tests that I've been mentioning, so tests of weak equivalence principle, which are done in the solar system, test of varying alpha, they are weak field tests. There is another area of expertise which relates to strong field tests of gravity. So tests in strong gravitational fields, so in neutron stars or even more so in black holes. So these tests play a role. The galactic center is a very good place to do this test, as some of you probably know. They're also a test of metric theories of gravity, and they complement the weak field tests that I've been talking about. And Actually, one of the science cases for one of the ELT instruments, so an instrument called Mikado, which is essentially the successor of the gravity instrument at the VLT, is to do these strong gravity tests using the black hole at the center of our galaxy. Uh, these are important tests as well, because if you expect uh, general relativity to break down at some level, one of the environments where this is presumably happening will be in strong gravitational fields. I don't have time to cover this topic, mostly because it's not my field. I know a little bit about it, but not a lot, so I'm not the best person to talk about them. But in any case, that they are complementary tests that can play a role in a lot of these theories. And to finish and motivate the class tomorrow, let me just give you one reminder, which is that essentially all cosmological constraints that we get, so all the cosmological data that we have and use to construct cosmological models, is model dependent. It comes with some assumptions. So when you say the universe is 30% matter and 70% dark energy, there's some assumptions behind it. You're probably assuming general relativity, or you might be assuming a flat universe, you might be assuming a homogeneous and mesotropic universe, and so on. So all these things and all these constraints have hidden assumptions behind them. And when you run your cosmological likelihood analysis, concerning these models, you have some priors that you put in, and so on. So that's something that we should be mindful of. Now, in that context, you could ask the question, what is the most model independent observation, that cosmological observation that I could do? What is uh, the best possible way that I have of observing the universe, of measuring something about the universe, which doesn't force me to make some of these assumptions? There is an answer to that question. The answer is called the redshift drift, and we'll talk about that tomorrow. But for today, this is where we stop. So let me stop sharing my screen, and as usual, I'm happy to take questions.
Thank you, Professor. Questions? No one? Everyone thinking about the lunch? Well, let me ask something. In the last slide, you talked about the strong gravity questions and research. Is there any research on gravitational waves of fine tuning or fine structure constant?
Not that I'm aware of. I think, or I suspect, let's say, that for variations at parts per million level, which is constrained at low redshift, um, the effects would be too small to be detectable in the near future, right? So at the moment we're detecting gravitational waves from black hole mergers, neutron star mergers, and so on. The constraints on the variation of alpha and these objects are not exactly parts per million level, but close to that. So any effect of that would be a higher order effect. Now you can think of the gravitational wave background as a whole. Um, there, I think there could be an effect of alpha variations. Um, I'm not sure how it would be distinguishable from other effects. I suspect that would quickly come into problems with degeneracies with other cosmological parameters, and not even other astrophysical uncertainties. Uh, but I'm not really sure. This is just my gut feeling, in a sense. Um, because the difficulty of a lot of these alpha measurements is that um, you need to find very clean systems. And by clean, I mean that Um, if you want to claim new physics, right? If you want to claim that you're seeing a different value of alpha, um, you have to be pretty sure that you've excluded unknown astrophysics, right? If you look at this in a messy astrophysical system, maybe you just don't know enough of the astrophysics of that system, and some of the astrophysics you don't know is contaminating your result. So in only very clean systems, you can be confident of making this kind of claim. Now, in that sense, the cosmic microwave background is a fairly clean system, although you have issues of foregrounds and so on. Spectroscopic measurements of alpha are a clean system if you have absorption clouds with the right properties. Um, these black hole mergers, I would guess, are not really a clean system in that sense, but it's just my guess. Uh, for the stochastic gravitational wave background, um, I'm not sure. Maybe it is a clean system, but by this definition, but maybe it's not. I mean, in any case, I mean to maybe address your question more specifically, I'm not aware of any study along those lines. So it might be an interesting project for someone to undertake, maybe at a master's level or PhD level for someone who's already knows a little bit about gravitational waves. Maybe there's an interesting thesis to be written there, but yeah, I'm not sure.
Perfect. Thank you. Any other question, Joyce?
Uh, Carlos, I got particularly interested in the constraints you showed from the temperature redshift relation on the omega m and W uh, plane because the temperature redshift relation in general it doesn't depend on the cosmological parameters unless you make uh, you assume some interaction between dark energy or dark matter with radiation. Is that what you did? What you did in that?
Right. Yeah. Yes. Yes. And in fact, you can see it. So let me give me a second to go back to that slide and then share it. Okay. So let me share the screen again. Okay. So as you can see here, the CMB temperature predominantly constrains the dark energy equation of state. It has basically no sensitivity to omega matter. Omega matter is only affected indirectly because of a normalization. But essentially, what's happening is that the temperature redshift relation is being changed. But this does have the advantage of breaking the degeneracy between the two parameters, right? Because you're getting data that essentially constrains W effective and is fairly insensitive to omega matter.
And
So,
this
so this is the role it plays. It breaks the degeneracy.
okay, in this W effective is the acting as interacting parameter between dark energy and photons and the CMB, right?
Yes.
Okay, so you have a coupling between dark energy and photons, and W is the interacting parameter. Is
Yes.
that correct? Okay, okay, I got it.
Yeah.
Thanks.
So I mean, you can write this um, as a coupling. I just rewrote it as the effective dark energy equation of state,
Okay,
just to make the plot more intuitive, let's say. But yeah, you're essentially constraining a coupling to be very close to zero.
okay, okay, good. Thanks.
Anyone? Nope. Well, before we end, let me just emphasize the useful of Discord. So maybe if you're shy and you don't want to question something, please use the Discord and you can continue discussing there. Okay? So let's thank again Professor Carlos.